Hey students, welcome back. We're going to be looking at piecewise functions and their limits. I wanted this to be its own topic because a lot of people have problems with piecewise functions. You may or may not have seen it in pre-cal. So let's just talk about what they are, how to graph them, and then we can kind of look at their limits. So first, we have f of x is equal to, and then we have this squiggly line, negative x. This means for x is less than or equal to 0. So if we're plugging in -1, we would plug it in here. We would plug it into negative x. If we're plugging in 1, this part is just for x is less than or equal to 0, so we can't plug in 1 there. We need to plug it in somewhere else. And in this next part, we see x squared is for a domain of x is greater than 0. So the example of 1 means we would plug 1 into x squared. Okay, so let's try to draw this. So negative x would look something like this. And once we get to 0, we note, okay, if it's less than or equal to 0, I'm going to put a filled in circle and then connect it to the rest of the graph. Okay, so this is negative x. Normally negative x would continue, right? We would go down here. But because our domain is just for less than or equal to, we're not going to include that part of the graph. Then we have x squared for x is greater than 0. X squared would go through 1, 1, 2, 4, and then straight on up. And this would have an open circle. Now the red part is kind of filling this. And let me do a different color so you can see that. So yes, the right side is kind of an open circle, but the closed circle is kind of filling that in. And then we go up with our quadratic. So this is how the graph would look. We'll talk about our limits later on. Let's keep graphing. Okay, next we have g of x. G of x is equal to 3 when x is equal to 2. Only at x is equal to 2. The way that we draw that is we go over to 2 and go up to 3 and just put a point there. And then the rest, this is when x is not equal to 2, we have x times x minus 2 over x minus 2. Okay, this might look kind of strange to graph, but we can kind of cancel these. So this graph's just like y equals x. So I'm going to graph that, y equals x. And then let's try that again, y equals x. At 2, we've got an issue. At 2, we can't plug in 2 because it's not part of our domain. So we have an open circle there. So our graph would look like this, a straight line with an open circle and a point right above it. Okay. Next, we have a 3-part piecewise function. When x is less than 0, we have 2x plus 3. So 2x plus 3 at 0. I know we can't really plug in 0, but we kind of can because we know that's where our open circle is going to be. So if we plug in 0, we have a y-intercept of 3. And then we have 2x. So we would have a positive slope of 2. So it would look something like this. Okay, I'm going to erase that little part here. Perfect. Okay. And then when x is between 0 and 3, we're going to have x squared minus 4x plus 3. If we plug in 0, that'll kind of tell us where our y-intercept is. If we plug in 0, we get 3. Okay, so that would be there. We kind of fill in that circle. And then I notice if I were to factor this, x minus 3, x minus 1, we have zeros at 3 and at 1. So I'm going to go ahead and mark those. And this would be actually an open circle here. And I'm just noticing this would also be an open circle at 3. So I'm going to go ahead and connect. I'm going to draw this graph. Open circle at 3 and comes somewhere down here. I'm not exactly sure where that is, but that's okay. And the left side and the right side actually left us with an open circle here. We have no value at x is equal to 0. The reason that is, this is when x is less than 0, not when x is less than or equal to 0. And this is when x is greater than 0, not when x is greater than or equal to 0. So this function h is actually not defined for x is equal to 0, which is okay. That can happen. So our function looks something like this. And then when x is greater than 3, but not equal to 3, once again, we have the square root of x minus 3. If we were to plug in 3, that would give us an open circle at 0. If we plug in 4, the square root of 4 minus 1 is 1. So it would look something like this. It's a square root function. Okay, so that's what our three-part piecewise function would look like. And then I think we've got another one down here. So let's take a look. We have, for x is less than or equal to 0, we have 2 over x plus 2. To be honest with you, I think I want to start with the second one. It's a little easier. So when x is greater than 0, we have negative x plus 2. When we plug in 0, we have negative 0 is 0 plus 2. So we have an open circle here, and negative x is our slope. So we're going like this. Okay, so our right side of the right side of this function would look like that. And then when x is less than or equal to 0, you notice we have a problem at negative 2. At negative 2, if we were to plug in negative 2, it would be 2 divided by 0. So we would have an asymptote. So I'm going to draw that. I'm going to draw the asymptote. And then if we were to maybe pick a point like negative 1, we would have 2 over negative 1 plus 2 is 2 over 1. So that's at 2. If we plug in 0 for x, we have 2 over 2 is 1. And this is less than or equal to 0, so this is a filled-in circle. Okay, and we've graphed a few rational functions now. We kind of know that they look like this. We're going to go up towards that asymptote from the right side. And on the left, maybe we plug in negative 3 just to see where this point is, but we know it's going to be looking something like this. So 2 over negative 3 plus 2 is 2 over negative 1, so negative 2. So we're going to look like something like that, and we're going to go like this. Okay, so here was our fourth and final graph, and now we need to talk about the limits. Okay, so we had the limit as x goes to 0 from the left of f of x. As we go to 0 from the left side, it's fine. It looks like we go towards 0. And the way, I kind of looked from the graph, algebraically, we can just plug 0 into the first part of our function. So we could say I'm going to actually erase this f of x and just say negative x. And we can do direct substitution. So negative 0 is 0. Okay, and I'm going to erase these f of x's here. And then from the right side, when we come from the right, we're actually going to be on this domain when x is greater than 0. So we're going to be plugging into x squared. There's no problem with x squared at 0, so we can directly plug in. 0 squared is just 0. Our limit as x goes to 0 of f of x is equal to 0 because both sides are the same. All right, we keep going. The limit as x goes to 2 from the left of g of x, will we plug into the top or to the bottom? We're going to plug in to the bottom, which is x over x minus 2 over x minus 2. If you've watched my video on algebraic limits, you know that we can't just plug in 2 immediately. We would have to cancel these out first and then rewrite this. The limit as x goes to 2 from the left of x This is 2. And we actually would do the same work for the next 2. The limit as x goes to 2 from the right is the same. It's the same process. We don't really need to think about this as a left and a right side because the left and the right side are both pertaining to this second function. Whereas in the first, the left side was the red function and the right side was the orange one. Here, since both are this blue line, we really don't need to think about the left side and the right side of limits. I'll finish writing that just so we have it. X goes to 2 from the right of x is 2. These would cancel. Okay, and so this is 2. This limit is 2. We do have a hole there, and we do have a different value at x equals 2, but that's okay. It doesn't affect our limit. Okay. The next one, we have a couple of different limits. So we're going to 0 from the left. So which equation do we need to look at? And 0 from the right. So 0 from the left is those values where x is less than 0. So we're going to plug into 2x plus 3. Directly substituting, we get 3. And from the right side, we're going to be looking in this domain because that's when x is greater than 0. So we have x squared minus 4x plus 3. Directly substituting, we get 3. Okay, and so the limit as x goes to 0 of h of x, because both of these sides are equal, is just 3. Okay, now we'll continue. We'll look at as x goes to 3 from the left of h of x, and I'm going to erase again. As x goes to 3 from the left, we're going to be using the second function because that's when x is less than 3. That's when x is just less than 3. Yes, when x is less than 0, we're going to use 2x plus 3, but we're just looking right around 3. That's why we're going to use the second function. So x squared minus 4x plus 3 equals, if we plug in 3, we have 9 minus 12 plus 3 is 0. And then from the right side, we're going to be plugging into the square root of x minus 3. Square root of x minus 3. Plugging in 3 directly, we get the square root of 0 is 0. So this limit is 0. So although we had three different equations writing this function, the limits when those functions met they existed, and they were equal to the left and right hand sided limits. So we didn't have any issues there. The last, okay, so as we go to 0 from the left of p of x, we've got to change. 0 from the left of p of x, the left-hand side, we're going to use 2 over x plus 2. Plugging in 0, we get 2 over 2 is 1. From the right side, we're going to be using the second equation, so negative x plus 2. Plugging in 0, we get 2. These are unequal. So we have some issue here at 0, where the orange function does not meet up with the green function. So this limit does not exist. Okay, and finally, are there any other potential problems? Is there anywhere else we might not have a limit? What we were checking was the border between each function, or functions, like in the last example where we had 3. We checked the border between the first and the second and the third. Now, yes, we've checked the border and there was a problem, but you all might see that there's another issue. At x equals negative 2, we have a vertical asymptote, and so our limit is not going to exist there either. So the limit as x goes to negative 2 of p of x does not exist. So it's important for us to check the borders, but also to look at the equations themselves. Usually we're not going to have a problem. However, in a situation like this, where the denominator is 0, we do in fact have an issue, and we do not have a limit at that point. All right, I hope this helped, and you know a little bit more about piecewise functions now. I'll see you next time.